Okay, so cardiovascular control works it's a very complementary subject with the respiratory system because both are upregulated as you become more active. And so let's add some more details on the metabolic side of things, okay? So we've already talked about this stuff, and in particular our focus was on how the lungs deliver oxygen and offload CO2 from the cardiovascular system. And the cardiovascular system provides this go-between the lungs and the muscle fibers, which have this elevated metabolic rate. But of course, the cardiovascular system also transports other essential ingredients for metabolism. And those include glucose, which emerges from the GI tract, as well as fatty acids. So remember all these details that we have about metabolism, and we have the ability to plug glucose in for glycolysis, which produces pyruvate, and then fatty acids can get plugged in at acetyl-CoA. In both cases, through the citric acid cycle and electron transport system, we get that high yield of ATP that's provided by aerobic metabolism. Of course, glucose and fatty acids come from other parts of the body. Fat provides a great source for those fatty acids, and through lipolysis, so the breaking down of lipids into fatty acids, then they are made available in the circulatory system. And again, this is sort of review. We didn't really talk about it with this iconography where we see the organs fitting in, but all these pathways were detailed before. And in those prior lectures, we also talked about how the liver is really important in providing glucose, and it does that through breaking down glycogen up here, converting amino acids into glucose. It also has this ability of recycling the lactic acid that's produced when you do anaerobic metabolism, and converting it back to pyruvate and then glucose, and then recycling it back again. So again, the liver is sort of this magical organ, which is really important for energy balance. All right, the point that I want to make here is that the cardiovascular system is central to all of this, okay? Both the chemical sources of energy that we use for ATP as well as those dissolved gases are transported through the cardiovascular system. So as metabolism on the right of this slide varies in its rate, then we need the cardiovascular system to also have the flexibility to vary its activity, its output. Transport of energy as well as oxygen is limited by that cardiac output. Okay, if the cardiovascular system cannot keep up with your activity, then you cannot maintain that activity. So the question for this lecture is, how is the heart controlled to do this, to vary its cardiac output? So again, we've got another situation where we're going to revisit some of those efferent organs, all the parts that we talked about for how the cardiovascular system works with, but now we're doing it in the context of control. And so for control, we've got the afferent side, the integration centers, and the efferent side, and we just want to articulate where all that is to see how these parts work together to maintain the cardiac output. What is cardiac output? Well, just like we talked about how ventilation is the product of the ventilatory rate and the tidal volume, you have the same basic relationship for the heart, where it's the heart rate and the stroke volume is what gives you your cardiac output. The cardiac output sets the flow rate for the body. Recall that flow rate is in liters per minute. That is the same thing as the cardiac output. And so before we talked about how through the law of continuity, you can predict the flow speed as the product of the speed and the cross-sectional area, and that is equal to the cardiac output. Okay, so our model for what the heart provides is that it sets the cardiac output for the circulatory system. Okay, so that equation also shows us the two variables that can be acted upon for this control. That is, the heart rate and the stroke volume are two aspects of the efferent organ, being the heart, and that can be varied. All right, we've only talked about the heart being controlled on a beat-to-beat basis, and we didn't talk about how the heart rate might change or the stroke volume. And so that is achieved through autonomic pathways, autonomic control. So even though the autorhythmic cells can generate the beat of the heart, the contractile cells can generate all that force, autonomic inputs to those autorhythmic cells are required in order to modulate or to control that heart rate. And we mentioned that briefly before in that, that lecture where I laid out an elaborate table. And I had mentioned that through parasympathetic inputs, you can get a reduction in beat frequency, whereas sympathetic will do the reverse. It'll elevate beat frequency. It also has this capacity to increase the stroke volume. Now, in addition to the heart, we of course have all the arterioles of the arterioles that influence the peripheral resistance of the circulatory system. And depending on where they're located, you can either have increases or decreases in the diameter of arterioles to shunt blood or have effects on the systemic blood pressure. Okay, so that's going to be the focus on the efferent side of things. So we're getting these inputs through autonomic pathways. We have those three candidates, sympathetic, adrenal sympathetic, and parasympathetic, acting in those regions of the cardiovascular system. So let's talk first about the heart, okay, and in particular the autorhythmic cells. So heart rate is driven by those autorhythmic cells in the SA node and the AV node. And we outlined this previously. It's the membrane potential of the autorhythmic cells. And we consider this in the context of how there are safety measures to keep your heart from exhausting itself. And there are some measures in the autorhythmic cells themselves because the action potential duration can't be varied. And that is true. However, the pacemaker potential can be varied. And so you can have two action potentials get closer and closer together in the interest of increasing the heart rate. And okay, so increasing heart rate, that's being chased by the bear. So you think sympathetic nervous system. That's the autonomic pathway that should be involved in elevating heart rate. And in fact, if you take an autorhythmic cell like this one and you expose it to norepinephrine, then you get a change in the membrane potential that's drawn in purple. So here we see that there's an elevated heart rate compared to the red curve. Even though there's no change in the duration of the action potential, we have both spanning the same period of time, and we can see that that membrane potential is uninfluenced by its exposure to norepinephrine. But what changes here is the pacemaker potential. Okay, and so here we have the previous action potential repolarizing right here, and then we're hyperpolarizing, but it begins its rise again, its gradual spontaneous depolarization at the same slope, but it does it at a point in time that's closer to this moment when it reaches threshold. So thereby decreasing the duration of the pacemaker potential, which is what we see right here. Yeah, question.
How would the norepinephrine affect the IF channels that would be responsible for the pacemaker?
Yeah, so the question is, how does norepinephrine influence the IF channels? That's a good question. So it turns out that what it does is it actually increases the duration of the IF channel, the IF channels being open. So you might think, since here we're shortening the pacemaker potential duration, you might think you might be decreasing that. But what happens is that they get activated early, and they kind of start the process of depolarizing the membrane earlier in this process than they otherwise would. So you can think of the IF channels as kind of impeding the repolarization that would normally happen at the end of the action potential, and that's because of the IF channels. So the IF channels do that in response to norepinephrine. Okay, so that's being chased by the bear, sympathetic nervous system. When you're relaxed, like, yeah, question? How are they reaching it at different times? Well, the way that I've drawn this is, since I wanted to put the two action potentials on top of each other, then this is effectively the time that's in common, like when they reach threshold. If I had sort of shifted the purple curve, say, over so that they were at this inflection point, then the reason for the shorter duration would be that it's effectively not repolarizing as much as the red curve. And so it's starting from a less negative point, and then it rises up at the same slope from that stage. And so that effectively just shortens that period of time. It's kind of arbitrary where they are shifted relative to each other. It just matters how you want to draw it on the slide here. And so I just overlap the two action potentials to do that drawing.
Question.
Yeah.
Would epinephrine have an opposite response?
Would epinephrine have
An opposite response?
an opposite response? Why would you predict epinephrine to do the opposite?
Because norepinephrine increases heart rate, so I was thinking epinephrine decreases.
No, so epinephrine is released by the adrenal sympathetic pathway, and so both sympathetic pathways kind of work to do the same sorts of activities. So they both are fight or flight responses, and so you should predict that elevated heart rate would happen in either case.
So you could use epinephrine here instead of norepinephrine.
So that would be a good test question. Would epinephrine work to do the same thing? And so what might you look for in the autorhythmic cells to resolve whether or not epinephrine could do the same thing?
If the IF channels open a bit earlier, then
You could look at the IF channels, but if you wanted to look, say, at the surface of those autorhythmic cells, there might be something there. The membrane, yes, but what I'm looking for in particular is whether or not there are, what type of receptors. So you have alpha receptors, beta 1s or beta 2s, then you have the opportunity for epinephrine to influence the autorhythmic cells. Okay, so when you're relaxed, your heart rate goes down. Your metabolic rate is not going to be as high, and so your heart rate can relax. And that's exactly what you see with input from the parasympathetic nervous system. In particular, the release of acetylcholine that comes from the parasympathetic system causes a depression in heart rate. Again, the action potential is the same here. We see the green curve is overlaid on the other ones, but what we have is an expansion in the duration of the pacemaker potential. Okay, so again, this is all old news in terms of pacemaker and action potentials, but what we're seeing here is how it gets tweaked by the autonomic nervous system. And so let's take those parts and plug them into a control system. So again, we're talking about the efferent side of things. We show that in red. And the sympathetic nervous system, with its norepinephrine release, is acting on beta 1 receptors. Okay, so that suggests that epinephrine could also activate the IF channels because we're talking beta 1s, and beta 1s have sensitivity to both. So that increases the duration of the IF channels, which elevates the heart rate. Okay, whereas the parasympathetic nervous system has the opposite effect, so we put that separate. That's an efferent pathway that is antagonistic to the sympathetic pathway. And through SA nodes, we get an elevation of potassium permeability. So this we did not detail, okay, but we can see that it is more hyperpolarized. And so it's consistent that you would have an increase in the permeability to potassium, and also a depression in the permeability for that cell membrane to calcium. Calcium, again, sort of behaves like sodium. And together, as a consequence of hyperpolarizing during the pacemaker potential, you get this reduction in the heart rate. All right, so that's what the autorhythmic cells do. They're setting the rate of the heart beating. But the contractile cells can also be controlled through the autonomic nervous system. And they do that, they are controlled in the interest of affecting the stroke volume. And the parasympathetic nervous system doesn't do that, but the sympathetic nervous system does. It has this capacity to increase stroke volume. And so how does that happen, or how do you see that? So we can return to another principle that we've seen before, and that is the Frank-Starling law. The Frank-Starling law, from experiments originally conducted on dogs, considered this positive relationship between the stroke volume, the blood that emerges from the heart, and the blood that is pushed into the heart, that is the end diastolic volume in the ventricle, which we see down below. So we get this positive relationship, and eventually it levels off. Okay, so that, again, is nothing new. We've seen that before. Now here, let's see, sympathetic nervous system. So if you're exposing those contractile cells that are responsible for this relationship, they're powering this relationship, to either norepinephrine or epinephrine, then you should expect an elevation in how much blood emerges from the heart, that is the stroke volume. And in fact, that's exactly what you see. So in the presence of epinephrine, you have the same volumes on the x-axis, but for any particular volume, you get a greater volume coming out the other end of the heart, the stroke volume. And so the red curve for every one of those end diastolic volumes on the x-axis, you're getting more blood coming through the ventricle. And again, this is achieved by the presence of beta-1 receptors in the contractile cells. And so one question would be, well, what is it that the cells are doing intracellularly in response to that stimulus that they're getting? Because recall, for contractile cells, they have a variety of safety measures to prevent you from driving those cells to exhaustion. And for example, we don't have the ability to have summation occur so that you can achieve tetanus like you do in skeletal muscles. But one thing that can be done is that the amount of calcium that's released during a twitch can vary in its magnitude. Okay, so twitches in cardiac muscle can vary in their tension, the maximum force that they achieve. And so in response to this norepinephrine release on the contractile cells, you get a higher amount of intracellular calcium, which generates more force when they're activated. The twitch tension goes up. It also turns out to decrease the duration of activation. Though these two properties are what we call an increase in contractility. Contractility means higher twitch tension, more force that emerges from all of the individual contractile cells, and as a consequence, there's a higher blood pressure that's achieved during systole, and you get a greater stroke volume. Okay, so let's plug that into our control system. Now we have norepinephrine release having an effect on the contractile cells, elevating their contractility, which in turn elevates the stroke volume. Okay, so let's do a clicker question. Okay, imagine this is an experimental manipulation type question. Imagine someone contracts a disease that degrades beta-1 receptors in the autorhythmic cells of the heart. What symptoms would you predict for this condition? So A is fatigue, B is an elevated heart rate when at rest, C is high blood pressure, D is all the above, and E is B and C. Okay, give me your final answer. Okay, so fatigue, you feel fatigued when your cardiovascular system doesn't deliver sufficient chemical sources of energy. If the circulation is insufficient to match your metabolic rate, then you feel fatigued. Okay, so then the question is that what you would expect when the beta-1 receptors are either not present or somehow aren't doing their job? And in fact, if you were to become more active, then you would want your sympathetic nervous system to elevate your heart rate. Okay, it's the sympathetic pathways that increase cardiac output. So that's why A is the correct answer, which 2/3 of you got right. Okay, so that's what we see right there. Okay. So, all right, so we laid out these parts early on in this lecture. We were talking about how we have these two efferent pathways. The heart side of things affects the cardiac output through those variables. But when you talk about the cardiovascular system, it is not just the rate of blood flow that matters, but also the pressure that is achieved by the left ventricle. So it is true that the left ventricle will generate higher pressures to increase stroke volume. But those high pressures have a variety of implications for the physiology of the rest of your body. I mean, the way the kidney works is it's all driven by hydrostatic pressure, right? That has a big effect. And there are a variety of effects of blood pressure. So as cardiac output goes up, so does the blood pressure. And you can approximate, or you can think of about blood pressure as the product of cardiac output and the peripheral resistance. And the peripheral resistance is, of course, primarily controlled by the arterioles that have, because of Poussey's law, this big hold over peripheral resistance because it's pushing that viscous fluid through pretty small vessels. All right, so both cardiac output, both the factors that we just considered, stroke volume and heart rate, but also the peripheral resistance, all of those are, have big effects on blood pressure. So why is blood pressure so important? Well, of course, it propels blood flow, as we just mentioned. But if it does so with pressure that is too low, then there are a variety of adverse effects. So you have hypotension, which can result in fatigue, ultimately shock and organ failure. That's just insufficient blood flow. Or if too high, you can also have heart failure, aneurysms, kidney failure, and a stroke. Okay, so again, we've got a situation where the body wants to be in a nice Goldilocks style intermediate state. And so a big aspect of cardiovascular control is to try to maintain a healthy blood pressure. So our cardiovascular control aims to achieve that at a healthy level. And we'll have to explain how that works next time. So have a good weekend.